So we've talked about solid circular shaft and we have talked about solid non-circular shaft. And we know that the angle of twist for a shaft of length L, that's this angle right in here when we apply a torque to it, that angle of twist is going to vary with the magnitude of the torque, the length of the shaft divided by the shear modulus and the polar moment of inertia. If we have a solid rectangular section with dimensions B and C, and B is larger than C, then the maximum shear stress occurs at the midpoint of the long side B and is given by this equation right here. Angle of twist for a shaft of length L, that is of rectangular cross section, is given by this equation right here. Easy things to sort out. So now what we have to do is we got to move from solid sections to non-solid cross sections. And in fact, what we want to do is we want to look at closed thin-walled tubes, meaning they form a complete loop. And so if we were to look at a closed thin-walled tube, we have to first consider what constitutes a thin-walled tube, and that is where the thickness is much, much less than the radius of the tube. The tube can have any sort of shape. It doesn't have to be elliptical or circular. It can be any shape you want it to be. And it has to be thin-walled, though, so that we can assume that the shear stress is constant across the thickness. So if we were applying a torque to this shaft like so, we would end up with a shear stress that ran around the outside, and its magnitude is tau. And so we have the shear stress that runs all the way around, and it's called a closed thin-walled tube because it closes on itself as you run around the shear surface. Now, it turns out that the torque that is applied is simply the integral of that shear stress along the length of that thin-walled tube. So we take that shear stress, we multiply it by the thickness, and we then integrate that on RDS. Well, it turns out that that torque then is equal to twice AM times the thickness times tau. So the thickness, you'll notice, is constant everywhere. It didn't vary with location. So it's a constant thickness tube. And tau is the average shear stress that's acting in there. And AM, what the heck is AM? AM is the area enclosed by the median line. So you look at the midpoint of this surface and you calculate all of the area enclosed by that midpoint. That's what AM happens to be. It's a relatively straightforward and simple calculation. If you then solve for the shear stress, you get that the shear stress is equal to the applied torque divided by twice the median area times the average wall thickness. The angle of twist per unit length is given by this equation. So if you want to know the total angle of twist for a thin-walled tube of length L, you would have to multiply this by L. So what is in this angle of twist equation? Well, we have the median area again. Notice that it's squared. We have the shear modulus. We have the wall thickness. And we have this LM. Well, LM is simply the length of the median line. You just measure the total length of that line, and you have very simple calculation to sort. So now what we're going to do is take a look at an example. We're going to look at a welded steel tube that is 40 inches long. It has a 1/8 inch wall thickness and a 2.5 by 3.6 inch outer cross-sectional dimension. We're going to assume allowable shear stress of 11,500 psi and a shear modulus G of 11.5 times 10 to the 6th psi. What we want to find is the allowable torque that can be applied to this cross-section and the angle of twist theta under that torque T. So what are we going to do? Well, what we have to do is take a look at our equations, how we relate shear stress to torque. And since we're trying to find the T allowable, we already know what the average allowable stress happens to be. We want to solve for T. So the allowable torque then would just be equal to the shear allowable times twice the median area times the wall thickness T. Well, we know what the wall thickness is. If we take a look at this section, we know that the wall thickness is 1/8 of an inch, or T equal 0.12 3.5 inches. There's my wall thickness. So I have one of the things that I need. Now I got to figure out the median area. So to figure out the median area, I need to come at the midpoint of this wall and calculate what area is enclosed by that midpoint. So I got to find all of this stuff in here. Well, if this outer boundary is 2.5 inches, and my wall thickness is 0.125 inches, and this side is 3.6 inches, then I know that all I have to do to find AM is I'm going to multiply 2.5 minus 0.125 inches by 3.6 minus 0.125 inches. And that gives me a median area of 8.253 inches squared. So now I have everything I need to find the allowable torque. The only thing that I have to put in there is what that allowable stress was. I said it was 11,500 pounds per square inch. So my allowable torque is simply going to be 11,500 pound per square inch. I'm multiplying this by 2. I'm multiplying it by 8.253 inches squared. And I am multiplying it by the thickness of 0.125 inches. That gives me my allowable torque of 23,728 inch-pounds. So there's my first answer. Now that I have my allowable torque, I can find my angle of twist. And in order to find my angle of twist, I have to multiply this angle of twist per unit length times the length L. I know that the overall length of this box is 40 inches. I already know what G is. I know what T is. I know what AM is. The only thing I don't know is this LM, so I got to figure that out. And in order to figure out what LM is, I'm going to go back and look at that box. I know that I have two. It is just the length of the median line. I have two of these 2.5 minus 0.125 inch lengths. That's this side and this side. And I'm going to have to add to that 2 of the 3.6 minus 0.125 inch lengths. That's this side, and that gives me an LM value of 11.7 inches. And now I have everything I need to figure out the angle of twist. My torque, as I said, is 23,728 inch-pounds. I'm going to multiply that by this 11.7 inches. I'm going to multiply that by 40 inches. I'm going to divide that by 4 times 11.5 times 10 to the 6 pound per inch squared. I'm going to multiply that by 8.253 inches squared, and that's by a thickness of 0.125 inches. So if we look carefully at all of that, 0.028 radians, and there are 180 degrees in pi radians. So if I multiply that by 180 and divide by pi, I get 1.625 degrees. So there is the angle of twist. We've now solved that problem. Well, now what if we have an open thin-walled section, as shown in figure 327 right here? By open, what we mean is that the shear stress does not form a closed loop around which it can run as we apply torque to this sample. And so we have two things to consider in these open sections. One is, what's the length of the median line that runs through it? And two, what is the thickness of the wall? So we're going to use C now for the thickness of the wall. And we find that if any of these are exposed to some torque T, we get a shear stress that varies with this equation right here. The shear stress varies as 3 times the torque divided by the median length and C squared, where C is the thickness of the section. G is the shear modulus, and theta is the angle of twist per unit length. So these are not recommended for carrying shear. Open thin-walled sections, you'll notice that the shear stress is inversely proportional to the square of the thickness, and that the angle of twist is inversely proportional to the cube of the thickness. So that's kind of an important thing. So it turns out that if you compare a closed, thin, round section to an open, that is a slitted circular section, you found that the stress in the sample with the slit is 12 times greater than the sample without the slit. And the twist angle, the angular twist, is 61 times greater. So this is not recommended. Open, thin-walled sections are not recommended for carrying torsional shear stress.